Super Secret Dissertation Proposal number 2. And the basic concept is to first build a small atomic unit, which we might think of as an artificial atom. Two of these atoms can be connected by a fixed rod, which is allowed to pivot. The ease with which it can pivot is called the rigidity, and can be set to any value between 0, which is free-moving, and 1, which is fixed. In this arrangement, two atoms are connected by a rod whose rigidity has been set to 0. As a force is applied to the atom on the right, it begins to pivot around the atom on the left. The color of each atom indicates the amount of force being exerted at that point. White represents no force, and red represents a force of 1, which is the maximum. The simulator is also able to display the force numerically. Larger lattices can be assembled, and the reaction of the lattice in response to external stimuli is governed by the configuration of each of the individual atoms. In the current model, this configuration is limited to the rigidity of each rod. The simulator can, however, also model the sensing and application of internal forces applied to each connecting rod. For the present demonstration, rigidity is the only parameter which will be modified. Throughout all these examples, a force is applied to the right-hand edge of the lattice. In this example, the rigidity of each rod has been set to 0, resulting in a drooping motion of the lattice. Without any constraints on the angle of the connecting rods, the system moves towards a simple linear state. The simulator can, however, specify a maximum angle, in which case the system behaves more as one would expect. In the simulator, we can adjust the rigidity of each rod. Here we set the rigidity to 1 on most of the rods, except for the ones on the left. The result is a semi-rigid sublattice on the right connected to a smaller, flexible sublattice on the left. The goal of this work is to design macroscale objects out of such lattices and be able to control their material properties through the manipulation of the configuration of their constituent artificial atoms. By so doing, it should be possible to design macroscale objects, so-called artificial matter, and control, for example, its response to external forces. One could, in theory, thus create objects that are stiff or flexible, hard or soft, or that remain hard and then yield to further force beyond some point, and so on. Despite this variation in macroscale behavior, all these objects would have the same principal underlying structure, namely an identical lattice of identical artificial atoms. The material is thus configured not by changing the lattice itself, but only by changing the characteristics of each atom. This would be managed by a highly distributed, parallel control system dispersed throughout the lattice, such as, for example, a cell matrix. One could, of course, explicitly engineer the resulting behavior of these macroscale materials based on a knowledge of what might be called matter engineering. A simpler approach, though, might be to use evolvable techniques. For example, to apply a genetic algorithm to the task of configuring a lattice to achieve some desired characteristic. In this example, a 5x10 lattice with a linear deformation is desired. Rather than conducting an analytical study of the physics of this complex system, one takes a genetic approach by creating a population of random materials, or individuals, 30 individuals in this case. Each individual is characterized by the rigidity values of each connecting rod. As each individual is subjected to an external force on its right edge, the resulting behavior is simulated and analyzed. The goal is, at each time step, to minimize the deviation in rod angle from atom to atom, i.e., to have the atoms be as collinear as possible within each row. This deviation is summed across 75 time steps, and the final sum becomes the fitness measure of that individual. Lower measures are thus more fit, with a measure of 0 corresponding to perfect linear deformation. After each individual is measured, the 5 most fit members are mated by selecting rod by rod a new rigidity for the offspring, randomly picked to be somewhere between the corresponding rigidity of each parent's rods. This results in 25 new individuals, which will include the 5 most fit individuals, resulting from each one mating with itself. 5 new random members are also generated, resulting in a new population of 30 individuals. A 2% mutation rate is applied to all matings. As can be seen, randomly generated materials do not generally exhibit the desired linear response. The population is evolved across 100 generations. In this simulation, the upper left window shows the evaluation of the current individual, while the other 5 windows show the behavior of the 5 most fit members. At the end of the 100th generation, member 29, one of the randomly generated members, can be studied in the simulator. As can be seen, its behavior is again not linear. We then study the behavior of member 0, the most fit member of the current population, and here we at last observe a nice linear response. In this window, we're looking at a blow-up of the most fit individual and studying its response to an externally applied force. The simulator can display the rigidity values, which seem to exhibit a nonlinear monotonic increase from left to right. This represents an example of evolved matter. How is this related to the cell matrix? The control system for this lattice of artificial atoms needs to have a number of characteristics. The control needs to be distributed throughout the system, and it needs to be localized. This is simply a consequence of the number of atoms and the fact that they each operate independently. Another characteristic is that if the system breaks into 2 pieces, each piece needs to be able to continue to operate autonomously. In other words, the breaking of the control system into 2 pieces, more or less along any arbitrary boundary, needs to result in 2 fully viable control systems. Similarly, if 2 systems are merged together in a join operation, the result needs to seamlessly turn into a single control system. And finally, we need faults to be localized so that if a defect occurs in the lattice or in the control system, only nearby atoms are affected. And all of these characteristics point clearly to something such as a cell matrix for the controlling substrate. The proposed work includes a number of different pieces. The simulator needs to be enhanced to be more accurate and to allow the application of forces other than at the external edges. Extension to a 3D model would lead to a more physically realistic system. One proposed modification to the actuation system is, instead of controlling the rigidity of each rod, leave all the rods fully movable and simply control the length of each rod. It has been suggested that this would be a more easy to implement system than one that actually controls the angle from atom to atom. Simulating the breaking apart and reconnection of sublattices is also an important enhancement. Further experiments in engineering materials or in evolving materials would certainly need to be done. And finally, there's a lot of room to explore the concept of dynamic materials, which are materials that respond to external stimuli in unusual ways. These are some of the areas that would be interesting to explore were this to be undertaken as a dissertation project. Thank you.